A 1 kilogram trolley moves right at 4 meters per second, hits an identical stationary trolley and latches to it. Without knowing the collision force or the contact time, can we find out what their shared velocity will be? Yes, if we analyse both trolleys as one system. The contact forces are internal to this system, but Newton's third law says they are equal and opposite. They act for the same time, so their impulses are also equal and opposite. One trolley's change of momentum is equal and opposed to the other's. Total momentum remains constant when the resultant external impulse is zero. During a brief collision, we normally treat the horizontal external impulse as negligible. The contact forces can then change each trolley's momentum without changing the total. Let's take right as positive. Before the collision, the total momentum is 1.0 multiplied by positive 4.0 plus 1.0 multiplied by 0. That gives positive 4.0 kilogram meters per second. Afterwards, their combined mass is 2.0 kilograms. Conservation of momentum gives 4.0 equals 2.0 v, so their shared velocity is positive 2.0 meters per second, to read the right. Only the total momentum of the chosen system is conserved. The momentum of each trolley changes. So does conserving momentum make this an elastic collision? No. For an isolated system, momentum is conserved in both elastic and inelastic collisions. So to classify the collision, compare the total kinetic energy. Before contact, only the first trolley is moving. 1/2 multiplied by 1.0 multiplied by 4.0 squared gives 8.0 joules. After contact, the 2 kilogram pair moves at 2.0 meters per second. 1/2 multiplied by 2.0 multiplied by 2.0 squared gives 4.0 joules. The remaining 4 joules have not disappeared, they have just been transferred mainly to internal energy as the trolley deforms, and to sound. Total kinetic energy has decreased, so the collision is inelastic. Because the trolleys stick together, it is the special case called a perfectly inelastic collision. Inelastic collisions do not always end with the objects joined, however. Now let's reset the same starting state and replace the latch with an ideal elastic bumper. For these identical trolleys, the first one stops and the second leaves at positive 4.0 meters per second. The total momentum is still positive 4.0 kilogram meters per second, and the total kinetic energy is still 8.0 joules, but this collision is elastic. In vehicle safety, controlled deformation can increase the stopping time. For the same change in momentum, this reduces the average force on an occupant. We saw this in our lesson on impulses. The same principle applies when objects move apart. Reset both trolleys at rest with a light compressed spring between them. Choose both trolleys and the spring as the system. Its initial total momentum is 0. When released, one trolley moves left at 3.0 meters per second and the other moves right at 3.0 meters per second. Let's take right as positive, and their momenta are minus 3.0 and positive 3.0 kilogram meters per second. They add to 0, so the total remains completely unchanged. Stored elastic potential energy has been transferred into kinetic energy, but no momentum has been created. The spring forces are internal to the chosen system. An explosion or a recoil follows the same rule. Starting from rest, if the separating masses are unequal, equal and opposite momenta means the smaller mass moves faster. For any collision or explosion question, define the system and choose a positive direction. Then add the signed momenta before and after. Set the totals equal only when the resultant external impulse is 0 or negligible, and then use the extra condition in the question. The objects may stick, a final velocity might be given, or the collision may be elastic. Momentum conservation describes the motion of the complete system. Comparing the total kinetic energy tells you whether a collision is elastic or inelastic. Next, we're going to connect these ideas to work, energy and power.